Somewhere right now, a quantum computer is trying to learn, not calculate, not simulate a molecule. Learn, the way a neural network learns, the way ChatGPT learns, except this machine is doing it inside a space with more dimensions than there are atoms in the observable universe. For a decade, physicists have chased the dream that this alone would be enough to end the age of classical artificial intelligence. Billions of dollars have poured into that dream. And in 2026, with the hype louder than it has ever been, we finally have enough evidence to ask the question honestly, is classical AI actually dying? Or has one of the most expensive bets in the history of computing quietly, spectacularly, not paid off yet? To understand why this question even makes sense, you have to understand the mathematical seduction sitting at the center of it, because it really is seductive, and it's not marketing nonsense, it's real physics. Stack together a modest number of qubits, the basic units of quantum information, and you don't just get more computing power the way you would by adding more transistors to a classical chip. You get access to a space that grows exponentially, doubling in size with every single qubit you add. 50 qubits gives you a space of over a quadrillion dimensions. 100 qubits gives you a number of dimensions larger than the number of atoms on Earth. And here's where it gets worse, or better depending on how you look at it, for the entire field of artificial intelligence. Machine learning, when you strip away all the buzzwords, is fundamentally the search for structure hidden inside spaces too enormous to explore by hand. Read that again. Quantum computers manipulate exponentially large spaces. Machine learning searches exponentially large spaces for patterns. Put those two facts side by side, and you can immediately see why serious, skeptical physicists, the kind who build entire careers trying to disprove their own field's biggest claims, have taken this idea seriously for more than 10 years. This is not chaos. This is strategy, at least on paper, and the strategy has a name. Quantum machine learning, or QML for short, refers to the use of a quantum computer to actually learn from data, to train models, to classify information, to generate new content faster or more accurately than any classical machine ever could. That's the headline version, the version venture capitalists get excited about, the version that shows up in breathless tech articles promising 2026 is the year everything changes. But there's a second, much quieter version of this convergence that almost never makes the headlines. And it involves using classical machine learning to help run quantum computers better, catching quantum errors, calibrating quantum hardware, decoding the noisy signals coming off fragile qubits. One version imagines quantum computers eating classical AI's lunch. The other version has classical AI quietly babysitting quantum hardware behind the scenes. As you're about to see, only one of these two stories is actually happening right now at scale, with real, independently verified results. And it might not be the one you expected. Let's start with the honest case for quantum machine learning, because dismissing this topic as pure hype would be just as dishonest as overselling it, and the real story deserves better than either extreme. In 2021, a team of researchers named Yunchao Liu, Srinivasan Arunachalam, and Kristan Teme constructed something genuinely remarkable, a classification problem built specifically from a mathematical concept called the discrete logarithm, on which they proved, with actual rigorous mathematics, that a quantum classifier has a provable speed advantage over any possible classical learner. Think about what that sentence actually means. This wasn't a claim. It wasn't a projection. It was proof, published in the prestigious journal Nature Physics, that quantum learning advantage isn't just theoretically possible somewhere out there in the abstract. It's mathematically guaranteed to exist, at least for this one specific, carefully engineered problem. For years, skeptics had argued that maybe quantum machine learning was fundamentally impossible, that the whole idea was built on a category error. This result permanently retired that argument. The door, at least for this one narrow case, genuinely opens. And then there's a second result, arguably even more exciting, because it points towards something that could actually matter in the real world, rather than just in a mathematician's carefully constructed thought experiment. In 2022, a team led by physicist Xin-Yuan Huang published a paper in the journal Science demonstrating an exponential advantage for quantum machines, specifically learning about quantum systems, using experimental data gathered from real quantum devices. Here's why this result deserves your attention far more than flashier headlines about quantum computers beating classical AI at generic tasks. When the thing you're trying to study is itself fundamentally quantum in nature, a molecule's electron behavior, an exotic new material, the output of another quantum sensor or quantum device, a quantum computer can absorb and process that information coherently in ways a classical computer structurally cannot replicate, no matter how much raw computing power you throw at the problem. This isn't a contrived academic exercise designed to make quantum computers look good. It's a genuine expanding category of real-world problems, and it grows wider every single time another quantum sensor or quantum simulator gets switched on somewhere in the world. So if the math checks out and the science is real, Why isn't classical AI already dead? This is where the story takes a sharp, necessary turn, the kind of turn that separates a documentary you can trust from one that's simply trying to sell you excitement. Because when you actually look at what happens when researchers try to run quantum machine, learning on the kind of data that actually matters to you and me, customer records, medical images, sensor readings, written text, ordinary real-world data rather than mathematically engineered puzzles, something uncomfortable emerges. As of 2026, after more than a decade of serious effort and an enormous amount of invested capital, there is still no demonstrated quantum advantage for machine learning on real-world data, not a contested one. Not a narrow, marginal one that experts still argue about. None that survives a genuinely fair comparison against well-built classical methods. Read that again, because it's the single most important number in this entire field, and it rarely makes it into the headlines. You don't have to take this on faith. You can watch this exact pattern play out directly in the peer-reviewed scientific literature. And 2 recent studies illustrate it with almost painful clarity. The first, published in the respected journal Scientific Reports in December of 2025, did everything a rigorous, honest piece of research is supposed to do. The researchers tested 5 separate datasets, deliberately injected noise, accounted for class imbalance, carefully selected features, and even added explainability tools so the results could be properly scrutinized. They pitted classical machine learning models directly against a quantum support vector machine, a quantum k-nearest neighbor classifier, and a variational quantum classifier, one of the most talked about quantum learning architectures in the entire field. If you only read the paper's abstract, you'd come away with words like resilience and potential, the kind of hopeful, forward-looking language that gets clipped into an exciting headline. But if you actually read the data tables buried inside the paper, a very different story emerges. Plain, old-fashioned logistic regression about the simplest classical classifier that exists, one that any first-year data science student could implement in an afternoon, outperformed the quantum methods on 3 of the 5 datasets tested. A random forest model won a 4th. The quantum support vector machine won exactly 1 out of 5. And the variational quantum classifier, the fashionable architecture at the center of so much recent excitement, scored between 14 and 23% on a 3-category classification problem. Think about what that number actually means. Random guessing on a 3-category problem should get you roughly 33% accuracy. The quantum model performed worse than flipping a 3-sided coin. On 2 separate binary classification problems in the same study, it scored below 50%, meaning it performed worse than an ordinary coin flip too. This is not an isolated embarrassment either. A second paper, posted as a preprint in May of 2026, ran essentially the same experiment using the famous MNIST handwritten digit dataset, the classic benchmark every machine learning student encounters early in their training. The headline results sounded genuinely impressive on the surface. A quantum neural network using 94% fewer parameters than its classical counterpart. But dig 1 layer deeper and 3 uncomfortable details emerge. Every single one of the so-called quantum models in the paper was actually a classical computer simulation of quantum behavior, not a real quantum computer at all. The convolutional neural networks being compared didn't actually contain any convolutional layers, a fairly significant mismatch when you're claiming an apples-to-apples comparison. And most damningly, achieving that headline parameter savings required roughly 1,200 times more computing time than the classical alternative, 33 hours of computation to save a grand total of 50 megabytes of memory, an amount of storage so small it wouldn't even hold a single high-resolution photo. This is not chaos in the sense of malicious deception. Neither of these research teams committed fraud, and neither paper should be read as an attack on the researchers involved. This is simply the ordinary, honest output of a scientific field, still testing quantum models on small classical datasets using computer simulations rather than real quantum hardware, and that distinction matters enormously. So what's actually going wrong here, mechanically, underneath the surface? There are 3 specific, well-understood reasons why quantum machine learning keeps stumbling on exactly the kind of data most people actually care about, and understanding each one tells you precisely where not to expect a miracle anytime soon. The first is what researchers call the input problem, or more bluntly, the data loading problem. To run any quantum algorithm on ordinary classical data, whether it's a spreadsheet, an image, or a block of text, you first have to load that data into a delicate quantum state. For most types of generic, real-world data, that loading process alone can cost as much computational effort as the entire calculation you were hoping to accelerate in the first place, quietly erasing whatever speed advantage you thought you'd gained. This isn't a new discovery. The physicist Scott Aaronson identified this exact trap in an essay a full decade ago, memorably titled, "Read the Fine Print." And despite 10 more years of research, the problem stubbornly remains unsolved. The second reason involves something researchers call the size of the prize, and it comes down to a distinction between two very different kinds of speed advantage. Many popular quantum approaches to learning and optimization lean on something called Grover's algorithm, which delivers what's known as a quadratic speedup rather than an exponential one. Here's why that distinction matters more than it sounds. A quadratic speedup is real, it's not fake, but it's also fragile, because once you account for the enormous overhead costs of running a fault-tolerant, error-corrected quantum computer, the kind that doesn't fully exist yet at meaningful scale, the underlying problem has to become astronomically, almost unimaginably large before the quantum machine actually pulls ahead of a well-optimized classical computer. In practical terms, that threshold often sits far beyond the size of any real-world dataset anyone would actually want to run. And the third reason is, in its own strange way, the most fascinating of the three, because it's less a limitation and more a discovery about where the true boundaries of quantum advantage actually sit. It's called dequantization, and the story behind it began in 2018, when a young researcher named Yuan Tang, still an undergraduate student at the time, single-handedly demolished one of the most celebrated results in the entire history of quantum computing. A famous quantum algorithm had promised an enormous speed-up for a type of recommendation system, the kind of technology that suggests what movie you might want to watch next. Tang built a classical algorithm running on an ordinary computer that matched the quantum version's performance almost exactly. Once you granted the classical algorithm the same kind of flexible data access the quantum algorithm had quietly been assuming all along. This wasn't a one-time fluke. Researchers have repeatedly found the exact same pattern recurring across the field, most recently in 2025, when classical techniques using something called random Fourier features managed to reproduce the performance of supposedly advantageous quantum kernel methods. Here's the genuinely interesting part. Dequantization didn't kill quantum machine learning as a field. What it actually did was draw a map showing researchers precisely where not to look for a real quantum advantage, which, through a process of careful elimination, is quietly sharpening exactly where a genuine defensible advantage would actually have to live. And that leads us directly to the honest, forward-looking part of this story, the part where quantum machine learning's real defensible promise actually seems to be hiding, rather than the part everyone gets excited about in viral headlines. If you take the one mathematically airtight proof of advantage, combine it with the genuinely compelling result about learning from quantum data, and lay both of them next to the hard boundary drawn by dequantization, a coherent, much more modest picture starts to emerge. The plausible quantum advantage isn't waiting patiently inside your company's customer spreadsheet or your personal photo library. It lives specifically in data and problems that carry a kind of structure classical methods simply cannot cheaply imitate genuine quantum structure or deep, unusual algebraic structure that doesn't show up in ordinary, everyday datasets. This is exactly why some of the most credible recent research has quietly abandoned the old strategy of trying to force quantum circuits into the shape of a traditional neural network. In March of 2026, the Quantum Machine Learning Research Group at Xanadu, a company widely respected for its own internal skepticism toward hype, proposed a fundamentally different strategy. Instead of asking how to make an existing neural network quantum, they asked a more basic question. What do quantum computers actually do naturally, on their own terms? And the answer led them towards something called the quantum Fourier transform, a mathematical operation deeply tied to the spectral structure hiding underneath many of machine learning's core techniques, including kernel methods and the way deep neural networks develop their internal biases. A companion piece of research pushed this idea further still, into learning over data with permutation-based structure, while that theoretical frontier continues its slow, careful advance. Something far more concrete, far more immediately useful, has actually been happening in laboratories and data centers throughout 2025 and 2026, and this is the part of the story that deserves far more attention than it typically receives. Because unlike the speculative promise of quantum computers learning to outperform classical AI, this convergence is real, measured, and already delivering results today. Remember that second, quieter direction we mentioned earlier, classical artificial intelligence being used to help run quantum computers better? That's not a future possibility. That's happening right now, and it's arguably the single most successful application of the entire quantum AI convergence to date. Quantum computers face a brutal, constant challenge, protecting their extraordinarily fragile qubits from errors caused by heat, vibration, and electromagnetic interference, errors that can corrupt a calculation in a fraction of a second if they aren't caught and corrected fast enough. This correction process demands enormous amounts of extremely fast, extremely precise computation running continuously in the background while the quantum processor works. And it turns out that classical, GPU-accelerated artificial intelligence is remarkably good at exactly this job. Consider what NVIDIA has built here. because it connects directly back to a story we've covered in depth on this channel before. NVIDIA's Q2Q software platform, paired with an interconnect architecture called NVQ-Link, allows classical GPUs to decode quantum errors in real time, catching and correcting mistakes before a fragile quantum state can collapse entirely. The performance numbers behind this system are genuinely staggering. NVIDIA's GPU accelerated decoding software delivers a 29 to 35 times speedup over industry standard error correction methods for a single processing shot, climbing as high as 42 times faster in high throughput scenarios involving many simultaneous error patterns. On Quantinuum's Helios quantum processor, this system achieved a reaction time of just 67 microseconds, a response so fast it exceeded the hardware's own 2 millisecond requirement by a factor of 32. IBM has been racing down a parallel, independent path of its own, developing a real-time error correction decoder built on specialized FPGA hardware, functioning as what industry insiders describe as a live runtime companion sitting alongside the quantum chip itself. According to IBM's own vice president of quantum, Jay Gambetta, speaking to Reuters, this FPGA-based implementation performs 10 times faster than what's actually required for live error correction, a result he personally called a big deal for making quantum computing genuinely practical in the real world. Here's why this distinction matters so much for answering the actual question posed by this video's title. This is not classical AI dying, being replaced, or being rendered obsolete by quantum computing. This is precisely the opposite. This is classical, GPU-powered artificial intelligence becoming absolutely indispensable to quantum computing's own survival and progress, embedded so deeply into the operation of these fragile quantum machines that without it, today's most advanced quantum processors simply couldn't function reliably at all. Jensen Huang himself, NVIDIA's own CEO, whose earlier public skepticism about quantum computing's near-term timeline we've covered before on this channel, ultimately built an entire strategic pivot around exactly this insight, that quantum computers would always need classical GPUs sitting right beside them, translating, correcting, and accelerating everything the fragile quantum hardware couldn't reliably do on its own. There's a third thread running through this story that deserves its own careful examination, because it sits in a genuinely fascinating gray zone between pure classical computing and pure quantum computing, and it's frequently, sometimes deliberately, mislabeled in ways that blur an important technical distinction. Photonic computing, chips that use particles of light rather than electrons to perform calculations, has produced some genuinely exciting, peer-reviewed research recently. A study published in the journal NPJ Unconventional Computing in late 2025 demonstrated that combining ordinary classical neural network layers with trainable, continuous variable quantum circuits produces hybrid networks with measurably improved trainability and accuracy, matching the performance of classical networks nearly twice their size, with those benefits holding up even under realistic hardware precision constraints. This is a genuine, credible, peer-reviewed result. But here's where the necessary skepticism comes in. The same skepticism this channel has applied before to claims surrounding China's photonic AI chips. In April of 2026, a company called Quantum Computing Incorporated announced that its Neurowave platform, a photonic reservoir computing system designed for fast, energy-efficient AI inference at the edge, in applications ranging from defense to healthcare to industrial monitoring, was fully ready for deployment. It's a genuinely interesting piece of engineering, offering real advantages in speed and power efficiency over traditional GPU-based systems for specific narrow tasks. But despite carrying quantum prominently in its own company name, this particular technology is fundamentally a classical photonic computing technique, one that doesn't necessarily rely on the strange quantum properties of superposition or entanglement at all. Even within genuinely quantum photonic research, the improvements being demonstrated right now remain modest, careful, incremental, not the world-shattering leap the title of this video might have led you to expect. A May 2026 research preprint tested a hybrid quantum classical photonic neural network architecture running on Quandella's Acela photonic quantum processor, and found that the hybrid models outperformed carefully matched classical baselines by roughly 0.6 to 8, tenths of 1 percentage point on standard image classification benchmarks. Read that number again, not 60%, not 6%, 0.6%, alongside slightly more consistent results across repeated trials. That is a real, measurable, scientifically meaningful improvement, and researchers in this field are right to be excited about it as a genuine proof of concept. But it is worlds away from the kind of civilization-altering leap implied by phrases like the end of classical AI. The same study identified thermal phase shifter reconfiguration, a purely mundane, unglamorous piece of hardware engineering, as the current dominant bottleneck limiting how fast these hybrid systems can actually run. So, pulling all of these threads together, where does that leave the actual question sitting at the center of this entire video? Is this really the end of classical AI? The honest, carefully researched answer, the kind of answer serious physicists working directly in this field would give you, if you sat them down and asked them off the record, is a clear and confident no, at least not for a very long time to come, and probably not in the specific way most viral headlines want you to believe. Standard matrix multiplication, the fundamental mathematical workhorse underlying essentially every deep learning system currently in existence, from the recommendation algorithm suggesting your next video to the large language model answering your questions, does not meaningfully benefit from quantum approaches using the hardware that exists today. And that single, unglamorous mathematical fact quietly undermines almost every headline promising quantum computers are about to replace the GPUs currently powering the entire artificial intelligence industry. Instead, the realistic, evidence-backed picture that emerges from 26's actual research, not its marketing, is fundamentally hybrid rather than replacement-based. Classical GPUs continue shouldering the overwhelming majority of AI training and inference work exactly as they do today, while quantum processors get explored carefully and incrementally for the narrow, specific subtasks where their unusual mathematical properties might genuinely offer some kind of edge. This mirrors, almost precisely, the broader hybrid quantum classical data center architecture we've explored in depth in earlier videos on this channel. The Open Compute Project's framework for physically integrating quantum processing units directly into existing data centers, and NVIDIA's NVQLink system connecting quantum hardware to GPU supercomputers through real-time interconnects. Nothing in any of that architecture suggests quantum computers replacing classical AI hardware. Everything in it suggests quantum computers being welcomed in as specialized, carefully managed guests inside a data center that remains, and will very likely continue to remain for the foreseeable future, fundamentally built around classical silicon. If you take away just one practical lesson from everything you've just heard, let it be this simple 4-question framework, because it will genuinely help you evaluate every single quantum AI headline you encounter from this point forward on this channel or anywhere else. First, ask whether the exciting result you're reading about actually ran on real quantum hardware, or whether it was simply a classical computer simulating quantum behavior, because the overwhelming majority of quantum machine learning results published today fall firmly into that second, far less impressive category. Second, ask what the classical comparison actually was, and whether it was genuinely well built and fairly tuned, because quantum models frequently only win against deliberately weak, poorly optimized classical opponents set up specifically to lose. Third, ask whether the claimed speed advantage would actually survive the real-world costs of loading data into the system and running proper quantum error correction. Because an advantage that quietly ignores those two enormous costs is, in practice, an advantage that only exists on paper. And fourth, ask whether the dataset being used was a natural real-world dataset, or one specifically deliberately engineered from the ground up to favor quantum methods, because a result on a carefully constructed, cryptographically structured toy problem tells you almost nothing meaningful about whether the same technique would work on your company's actual data. Perhaps the most telling detail in this entire story is who exactly is being cautious and who is being loud. In industry roundups gathering expert predictions for 2026, the people who actually design and physically build quantum hardware for a living consistently describe new claims of exponential quantum learning speedups using words like speculative, while quietly directing their genuine near-term enthusiasm toward far less flashy applications. Error. Correction, hardware calibration, learning directly from quantum data sources. Meanwhile, it's frequently marketing materials, funding pitches, and search engine optimized blog content, rather than the peer-reviewed researchers actually running these experiments day to day, that keep proclaiming 2026 as quantum AI's long-awaited breakthrough year, when the people physically building these machines with their own hands are consistently more cautious than the online content promoting them. That gap itself is a signal worth paying close attention to, and it tells you almost everything you need to know about where the real evidence-based frontier of this technology actually sits today. None of this means the underlying science isn't worth following closely, and it certainly doesn't mean this entire field is nothing more than empty hype dressed up in exciting language. The mathematically proven speed-up from 2021 is real. The exponential advantage for learning from genuinely quantum data is real, and arguably one of the most exciting, quietly underappreciated results in the entire field. The careful hardware-aware research coming out of groups like Xanadu, exploring the natural spectral structure quantum computers seem uniquely suited to exploit, represents exactly the right kind of question for serious researchers to be asking right now. and the deep, increasingly indispensable integration of classical AI into keeping quantum hardware alive, stable, and error-corrected represents a genuine, measurable, rapidly accelerating technological revolution, just not remotely the one implied by a headline promising the death of classical artificial intelligence. Quantum computing and classical artificial intelligence are not, as of the middle of 2026, locked in a winner-take-all battle for supremacy. They're becoming something closer to permanent, interdependent partners, each one propping the other up in specific, carefully bounded ways precisely where its own particular strengths happen to shine brightest. So no, this is not the end of classical AI, not this year. And based on everything the actual physics and the actual published research currently tell us, probably not for a good many years still to come. But somewhere in the years, directly ahead, on exactly the kind of narrow quantum-structured problem this research keeps circling back to, learning from quantum data, at exploiting genuinely unusual algebraic structure that classical shortcuts simply cannot fake. Expect this field to finally produce its first quantum machine learning advantage that survives a truly fair, rigorous fight against the best classical methods available. When that day finally arrives, and based on the trajectory of this research, it increasingly feels like a matter of years rather than decades, that will be a headline genuinely worth believing, rather than one worth scrolling straight past. If you want to understand exactly what that eventual breakthrough might look like and which specific research teams around the world are closest to actually reaching it, that's precisely the story we'll be tracking closely as it continues to develop. So make sure you're subscribed before that day finally arrives, because judging by the accelerating pace of everything you've just heard, it may not stay a distant speculative promise for very much longer. Before you go, I want to know what you genuinely think. Based on everything covered in this video, do you believe quantum computing will eventually transform artificial intelligence in a meaningful, measurable way? Or do you think classical AI and the GPUs currently powering it will continue to dominate for the vast majority of your own lifetime? Leave your honest answer down in the comments below, and as always, I rate every single one.